The next topic that we're going to look at is Leibniz theorem. Leibniz theorem involves a differentiation of an integral. Differentiation of a definite integral, which is a function of x. Usually, a definite integral has constant limits. So once you do the indefinite integration of a function, you get a function. Once you put the limits, once you put the constant limits in the place of x, you get a constant number. For example, if the limits are some functions of x, the integration variable is t. So integration of f of t dt, integrated between phi of x and psi of x. Because the limits are functions of x, the integral will be a function of x. So if you want to differentiate this, so d by dx of integration of phi of x to psi of x f of t dt is equal to, the formula is f of psi of x. First, in the function, in the place of t, you have to put the upper limit, that is f of psi of x, into the differentiation of the upper limit, minus f of phi of x into the differentiation of the lower limit. So this is the most useful form of Leibniz theorem. So d by dx of integration phi of x to psi of x, inside the integration you don't have any extra. The integration is f of t dt. Then you just need to put the upper limit in the place of t, f of psi of x, into the differentiation of the upper limit, minus f of the lower limit into the differentiation of lower limit. So this is a special case of Leibniz theorem, which is the most useful case. Next, you have a general case of Leibniz theorem. D by dx of integration of psi of x to integration of phi of x to psi of x, f of x comma t dt, is an implicit function. That is, you have an integration variable which is in terms of t, and you also have an x in the function. You also have an x in the function. So if x can be separated, it can be brought outside, and the integration can be completely in terms of t. But if these two cannot be separated, the formula will be d by dx of integration of phi of x to psi of x, f of x comma t dt, is equal to, the first term is integration phi of x to psi of x. This d by dx comes inside and becomes dou by dou x. So dou by dou x of this function. This is in terms of both x and t. So whenever you differentiate with x, you do the partial differentiation. That is assuming t as a constant. So dou by dou x of f of x comma t dt, that is one term, plus in the next term, this looks similar to the previous formula. What you do is, in the place of t, you put psi of x, that is f of x comma psi of x. Wherever you have x, you don't need to do anything with it. Wherever you have t, you need to put psi of x in the place of t. That is, you need to put upper limit in the place of t, f of x comma psi of x into the differentiation of the upper limit, minus f of x comma phi of x into phi dash of x. So this is the general case of Leibniz theorem if you have an implicit function inside the integral, which has both x term as well as a t term. The next special case of Leibniz theorem is d by dx of integration a to b, f of x comma t dt. The limits are constant this time, but the function inside the integral is an implicit function. That is, you have an x as well as t. T is the integration variable. So you get, when you integrate this, you get a function of x as well as t. And when you put the constant limits in the place of t, you get a simple function in terms of x. So what is the differentiation of that function? So you just need to apply the previous formula in a special case. So d by dx goes inside and becomes dou by dou x. So integration a to b, dou by dou x of f of x comma t dt, plus, because the limits are constants, this term and this term become 0, and this whole term becomes 0. So you don't have any other term. So this is the general case. So there are two special cases. The first special case is that the limits are the functions of x, but you have only t inside the integrand. The next special case is you have both x and t inside the integrand, but the limits are constants. So in one case you don't get this, you only get this. The next case you won't get this, you get only this. So obviously if the function is only in terms of t, if you do dou by dou x, this becomes equal to 0 for this function. In this case the first term becomes 0. In this case the second term becomes 0. So let us investigate with the help of some examples how to use this Leibniz theorem. So let us take an example where you need to find d by dx of integration x squared to x cubed 1 by log t dt. So as you can see, this is a special case. The integrand is completely in terms of t. So you don't have an x inside the integrand. So I'll use the first formula which says that d by dx of integration phi of x to xi of x f of t dt is equal to f of xi of x into xi dash of x minus f of phi of x into phi dash of x. So if you apply this formula in this question, this phi of x on comparison is x squared, this xi of x on comparison is x cubed, this f of t is nothing but 1 by log t. So d by dx of integration x squared to x cubed 1 by log t dt is equal to, first you need to put the upper limit in the place of t, that is 1 by log x cubed times the differentiation of the upper limit is 3x squared minus, next you need to put the lower limit in the place of t, that is 1 by log x squared times the differentiation of x squared is 2x. So if you want log x power 3, this 3 comes out, that is 1 by 3 log x times 3x squared, this 3 and 3 gets cancelled, minus log x squared is 2 log x, 1 by 2 log x times 2x, this 2 and 2 gets cancelled. So that is equal to x squared minus x by log x. So this will be the differentiation of integration x squared to x cubed 1 by log t dt. In this question, you're given that if integration sin x to 1 t square f of t dt is equal to 1 minus sin x for all x belongs to 0 to pi by 2, then f of 1 by root 3 is equal to how much? So first what we do is, if I want f of 1 by root 3, if I find f of x, that will be very easy. So what I do is I'll try to find f of t. So for that what I do is I'll differentiate this equation on both sides, because this is equal to this. The differentiation of this should be equal to the differentiation of this. So d by dx of sin x to 1 t square f of t dt is equal to d by dx of minus sin x is minus cos x. So now I'll apply Leibniz theorem to do this differentiation. So the function inside the integrand is completely in terms of t. So it's not an implicit function. So directly we can use the first case. So first what we do is we put the upper limit in the place of t. It is 1 square times f of 1 times the differentiation of the upper limit is 0 minus, I'll put the lower limit in the place of t, is sin square x into f of sin x, sin square x into f of sin x into the differentiation of the lower limit is cos x is equal to minus cos x. So this is 0. So this implies minus sine square x f of sin x times cos x is equal to minus cos x. So this cos x and cos x gets cancelled. This implies f of sin x. This minus and this minus also gets cancelled. F of sin x is equal to 1 by sin square x. So if sin x goes inside, 1 by sin square x comes out. This implies f of x is equal to 1 by x square, right? If sin x goes in, 1 by sin square x comes out. If x goes in, 1 by x square comes out. So once you get f of x, what is f of 1 by root 3? So 1 by root 3 whole square is 1 by 3, which is equal to 3. So f of 1 by root 3 will turn out to be 3. In this question, you are asked to find limit x tends to 0, 1 by x cubed times integration 0 to x square sine root t dt. So this is the most standard type of question on Leibnitz theorem. So this is limit x tends to 0, integration 0 to x square sine root t dt divided by x cube. So now if you do the direct substitution, so if you put x is equal to 0, so integration 0 to 0, so both the upper limit and lower limit are same, hence this integral is going to 0. So you get 0 by 0 form. So you get a 0 by 0 form. Hence, by L'Hospital rule, this limit can be found out by differentiating the numerator as well as the denominator. So this is same as limit x tends to 0, d by dx of integration 0 to x square sine root t dt divided by the differentiation of x cube is 3x square. That is equal to limit x tends to 0. So d by dx of, this is a function completely in terms of the integration variable t. So we use the general Leibniz theorem. First case, first you put x square in the place of t, is sine of root of x square is x, sine x times the differentiation of x square is 2x, minus you put the lower limit sine root of 0 into the differentiation of 0 is 0. So this is getting cancelled by 3x square. So 1x and 1x gets cancelled. That is equal to 2 by 3 times limit x tends to 0 sin x by x. So we know that sin x by x as x tends to 0 is 1. So the answer is 2 by 3.